Okay, so this is the 2.7, and it's day 21 of the unit, but it's 2.7. It's linear quadratic solution. So up until now, we've pretty much been doing lines and lines, putting those together. And now what we're going to do is combine lines and quadratics. It's really the same basic stuff, but the algebra does look a little bit different. So we're going to start with the basics, which is checking a solution. So remember that a solution of a system has to satisfy all equations in the system. And by satisfy, that means that the left has to equal the right. In a system where you've got different types of shapes, it's less likely it's going to work on all of them. You know, lines and lines, you're not really going to get a bad solution, but with this one, you could. So let's do an example. Let's say that you get point P for and it's -3, 4, and you want to know, is it actually a solution? Okay, and the system that we're going to be working with has the line y equals 2x plus 10, and the quadratic 3x squared minus 5y squared plus 2y equals 45. Which this one isn't a quadratic. This one's actually a different shape. Most of what you're going to be doing is linear quadratic, but it doesn't really matter because the process is identical. You're going to substitute the point into the equation and see if the left equals the right. So if we do it into the first equation, substitute 4 for y. So 4, does that equal 2 times -3 plus 10? You always do the easy one first, because if you're going to find a problem, better to do it on an easy one. So -6 plus 10 is 4. So yeah, it works in the first equation. So now we got to try it out in the second equation. So again, we're going to substitute in for x and y. So 3 times -3 squared minus 5 times 4 squared plus 2 times 4. Does that equal 45? All right, and the biggest mistake that people make on this one is they forget to do the squares first. You want to do the exponents first and then multiply. So we're going to do -3 times -3, which is +9. And then we're going to do 4 times 4, which is 16. And that's your first wave, is just to do the powers. Now we're going to actually multiply. 3 times 9 is 27. -5 times 16 is -80. 2 times 4 is 8. So we did the powers, we do the multiplying, and last we add. And this actually ends up being -45. Well, -45 is not equal to 45. So the answer to the question, is this the solution, is no. It didn't work in the second equation of the system. So that's how you check a solution, which is pretty much like we always check solutions. You just have to be a lot more suspicious when you have a variety of equations. Okay, so Roman numeral 2. Types of solutions. So I want you to draw 3 little pairs of axes across the page. Okay, and this is not an all-encompassing thing, but it does show you the 3 types of solutions. So on all 3 of them, I want you just to draw just a medium-sized parabola opening upward. Okay, so the first case is where your linear equation completely misses the parabola. It doesn't even intersect with it. So in that case, there would be no real solution. When you solved it, you might get an imaginary solution, but you won't get a real solution because they never intersect each other. So that's possibility number one. Possibility number two, which is probably the most common, is that the line cuts through the parabola in two different places. So on that case, you're going to get two real solutions. The third case, which is much more rare, but it does happen, is that the line intersects the parabola at only one point. So it just barely touches it at one point. That would be one real solution. That happens, but not very often, because it's got to be a pretty exact combination of circumstances. Okay, so those are the three types of solutions you can possibly get with this. All right, let's go on to Roman numeral 3. Solving algebraically. And the example we're going to do is y squared minus 7x plus 3 equals 0. That's your parabola. And then 2x minus y equals 0. When you have to solve a system where the equations don't line up with each other, they're not the same shape, you're really kind of stuck with substitution method. Because the equations are so dissimilar, you can't do linear combination because nothing lines up. So in this case, you would want to pick the easy one first, preferably the lonely only, which is the y. So I would start with that one. So 2x minus y equals 0. And you'll want to solve for y. So you can do this a number of ways. One way is to add y to the right, and then just flip the sides, y equals 2x. So solve the easiest one you can figure between the two and get your first answer. Okay, so now I'm going to write the one we haven't used yet, y squared minus 7x plus 3 equals 0, and we're going to substitute 2x in for the y. So that's going to give us 2x quantity squared minus 7x plus 3 equals 0. Now we have one equation with just one variable. So we're going to solve for x. So 2x times 2x is 4x squared minus 7x plus 3 equals 0. And at this point, you can choose what you want to use to solve. How you want to solve it, I mean. So you can factor it, you can do quadratic formula, you can do completing the square. Those are your three options when you have an x squared term in there. Of course, you want to try to factor if it's possible, because that's the fast way. And this one actually, thankfully, does factor equal to 0. The factors are 4x minus 3 and x minus 1. So you set each factor equal to 0. So 4x minus 3 equals 0, x minus 1 equals 0, and you solve. And I'm just going to put ... because you all know how to do that. So x equals 3/4 and x equals 1. Now here's where this is different. Normally when you learn substitution, you only had one answer. We actually have two. So you have to sub each of them into the first equation to figure out what y goes with both points. So let's start with the first one. We're going to substitute in 3/4 for x. So y equals 2 times 3/4. And that gives us y equals 3/2. So that solution would be 3/4 for the x, 3/2 for the y. And they would be an ordered pair. Okay, then we have to substitute in the other solution. So y equals 2 times 1, which is 2. So my other solution is 1, 2. Those would be your two answers. So obviously with this line and this parabola, the line passed through the parabola in two places, so you got two answers. You won't ever have three answers or more, never. It'll either be no answer, one answer, or two answers. The way you can write that answer is xy is an element of the set containing, and then you list the pairs. So 3/4, 3/2, and 1, 2. So you still use roster notation to list your solution. It's just that so you still do ordered pairs, but you're going to use roster notation so that you can list more than one ordered pair. So there's your ordered pairs and then rosters with the braces. Okay, so last thing we're going to do is solve graphically. So I'm going to start at the top of a new piece of paper because parabolas do take a little bit of algebra work. Okay, Roman numeral 4, solving graphically. Okay, and our system is y equals x squared minus 6x plus 3, that's the parabola, and y equals 2x minus 13, that is the line. That is your system. Okay, so I'm going to pick the parabola first, to graph first. So y equals x squared minus 6x plus 3, that's our parabola. So remember that the vertex of the parabola in standard form, the x-coordinate has the formula -1 times b over 2 times a. So we're going to calculate the x-coordinate of the vertex. So that would be -1 times -6 over 2 times 1 would be 6/2 or a 3. That's the x-coordinate of the vertex. To get the y-coordinate of the vertex, there isn't a formula. You're going to substitute in the x and then solve for the y. So we're going to substitute 3 into the equation. So y equals 3 squared minus 6 times 3 plus 3. And again, I'm going to skip ahead a little bit. That ends up being -6. So from those two, our vertex is 3, -6. Other things that we know about this parabola is the a value is positive, so it's going to open up. The a value is a 1, so it's going to be a nice medium-sized bell on the parabola. Okay, so let's come over here, and our vertex is 3, -6, so you might want to push your x-axis up a little bit and give yourself a lot more room down below. So 3 to the right, 1, 2, 3, down 6, 1, 2, 3, 4, 5, 6. That's your vertex. Okay, now we need to come up with 2 pairs of points. So I'm going to make a extended H chart over here. And you can pick symmetrical pairs. So if I go 1x to the right, it's a 4. 1 to the left is a 2. So 4 and 2 should have the same exact y value. And if I go 2 to the right, that would be 5. And 2 to the left would be 1. And those should have the same y value. Okay, so I'm going to substitute 4 into the parabola. So x squared, so 4 squared minus 6 times 4 plus 3. So 16 minus 24 is -8, plus 3 is -5. And since 2 is its symmetrical partner, that should also be -5. Now for the next pair, I'm going to be lazy and substitute in the 1 instead of the 5. So 1 squared minus 6 times 1 plus 3. 1 minus 6 is -5. -5 plus 3 is -2. So the 5 and the 1 should be -2. All right, go ahead and plot those and draw your parabola. 1, 2, 3, 4. Okay, let's do the line. So your line is y equals 2x minus 13. It's already in a nice graphable form, so we don't have to do anything to it algebraically. Now we want to know if it's going to cross the parabola. So when you focus your x values, you want to look to where it crosses over here. Now this is down at -13, which is like way the heck down here. I actually can fit it on my graph. 6, 7, 8, 9, 10, 11, 12, 13. And then it's got a slope of 2. So it looks to me like it's either going to miss or barely touch. So I'm going to be looking for x values that are going to give me a nice line going this way. So I'm not going to pick a 1 or a 2. That'd be clear down here. And I need to know where they cross. So I would be looking at 5, definitely, and maybe 6, and maybe 7. And then I'll kind of see how it's looking. So if I put the 5 in, 2 times 5 minus 13 is 10 minus 13, or -3. So 5 negative, oh, look at that. So it doesn't look like it's going to cross up here. So what about 4? I'm going to change this to a 4. So 2 times 4 minus 13 is 8 minus 13, or -5. Aha, right there. So I've got enough values, I can see it's just going to touch at the 1 point. And if you use a straight edge, it's pretty obvious that's the only point it's going to share. So your solution is 4, -5, which is right there. And usually you want to indicate the solution on your graph, write solution and write the coordinate. Especially if you're taking your state test and they want you to solve by graphing, you don't want to just make a graph and tell the person grading, you find the solution. No, you want to show them, I know where the solution is, it's right there. So that's kind of the process for solving graphically. Again, I usually do the parabola first because that is the harder shape to get the values. And then for the line, I kind of just pick it depending on how it looks like it's going. And you want to pick strategically so you don't end up having to do 20 points. You do 2 or 3. When in doubt, though, crank a few more points. Line equations are easy to find points. So any questions about that, solving graphically?